Okay, all right. So let me go through a quick recap of what we talked about last week. So we were looking at factor analysis model on Friday, which is one form of latent variable models, right? And the idea there is that there is something that we observe, which is xi, right? And we assume that xi depends on a hidden variable zi, and zi itself is a vector of random variable, vector of certain number of elements. And typically we fix the number of elements in zi, right? We say that zi has L elements, whereas xi has capital D elements, right? And then xi, there's a PDF for xi which is dependent on zi, right? That's the basic idea behind latent variable models, is what you observe depends on zi, or depends on some hidden variables, and they are connected to each other through this linear combination. So W is what we call a D by L loading matrix, which essentially does this combination, linear combination of your L elements in Zi and gives you D elements, right? So if you look at the reverse problem, it looks like some kind of a, I'm sorry, it looks like a dimensionality reduction problem, right? Because if you go back to the slides for factor analysis, this is the forward problem, right? Given Zi, what is Xi? But you can also then compute what is Zi given some Xi, right? So that's the inference problem. And we saw that that also comes out as a Gaussian, because everything here is a Gaussian. When you mix Gaussians, they always end up into Gaussian. So that's the beauty of them. But the point is that you can get Zi given Xi. Now, since Zi has only L elements, so you can think of this as a form of dimensionality reduction. So you are giving it a vector of D attributes, and then you're getting back a vector of smaller attributes, right? And then we looked at an example last time, and we saw that those factors, right, those individual components in Zi, which we call factors, they have some you can interpret them, right? So that's the idea, and that is why factor analysis models have been very popular in statistics, especially in psychometrics, where they try to understand behavior of people by observing certain things. So typically what they do is they take a survey of many people. So let's say somebody comes to this class, hands you a survey with 100 questions, right? But all of those questions might not be independent of each other. So so within them, they might be talking about some hidden latent concepts. So then what they do is they run factor analysis on that to identify these L common factors, right? So that is the general idea, right? Then I also briefly mentioned that factor analysis can be thought of as this root concept, and if you put certain constraints to that, it looks like some other models that have been independently developed, all right? So for example, if you assume that we do not have a Gaussian distribution for Zi's, then it becomes what we call independent component analysis. We will not look at it in this class. It's also known as ICA, where the idea is that you have some data in d-dimensional space, and you're trying to identify L smaller number of dimensions which are independent of each other, right? Because that is the key, right? If you remember, in all of our machine learning, we always assume that all of our attributes are independent of each other, right? But in reality, that might not be true, because what you observe, things might be connected to each other. But if you do things like ICA, you can convert them into these independent components and then analyze them. So that's a general idea, right? But what we are going to talk today is what we call principal component analysis. And there is one form of principal component analysis which is called probabilistic principal component analysis, which can be thought of as a special form of factor analysis, all right? Principal component analysis is a mathematical technique that has been there for many decades, or maybe a century. I want to check that. But anyway, so that was independently developed somewhere, right? But it does not have any probability in it. It's not a stochastic or a random or a statistical method, right? But what it does is, so PCA by itself does not have any randomness to it. So if you run PCA, you get the same answer. But there's a form of PCA called probabilistic PCA, and you can see, we can show that, and we will do that later on, is that factor analysis, a special form of factor analysis, is nothing but probabilistic PCA, right? And then there are some constraints. If you put, then it becomes looking like PCA. But today we are going to look at PCA as itself, right? And then later I'm going to talk about how it is a sort of a factor analysis model. Oh, sorry, how is it a latent variable model, all right? So let's start with that. So there are many ways to understand PCA. In particular, there are two views. One is using PCA or principal component analysis as a way to reduce the dimensionality of the data. All right. So if you have data in d-dimensional space, if I want to reduce it into two-dimensional space or three-dimensional space, then you can use PCA as one of the concept, right? Another way to understand PCA is the latent variable model. So we'll do both today, right? So let's start with an example. So let's say this is a data set that you have. You have data in two-dimensional space, and you have 5 points in that space, right? Now, I want to represent them in one dimension. The embed is not a right word, but essentially you want to, instead of storing data in two-dimensional space, I want to represent it in one-dimensional space, okay? Now, the first question that you should ask is why, right? Why do you want to reduce? So one reason could be that you want to compress it, all right? So you want to reduce the size. So if you have data in two-dimensional space, so if you have 5 points, you have to store 10 floating point values. If you can reduce it in one-dimensional space, you have to represent it in using 5 floating point values. So that's easy. The second thing is that oftentimes what happens is that when you're looking at very large dimensional data sets, there is a lot of noise in the data. So hopefully the goal is that you reduce it so that you remove some of that noise. So there are all those reasons to do dimensionality reduction. Another reason is when you have to visualize, right? So given human eye, we are constrained to visualizing things either in 3D or 2D, right? But oftentimes your data occurs in a very high dimensional space. So how do you, if you want to visualize this data set, you can't do it in that high dimensional space. So somehow you have to bring it down, right? So let's start with this simple example. So let's say I have this data set, right, in two-dimensional space. And I want to represent it in one-dimensional space. So from R2 to R1. So there are many ways to do that, right? So for example, one way to do that could be that I just use, so let's say this is dimension 1, this is dimension 2, right? One way is I just use the one of the dimensions as your dimension, right? That's not a very intelligent way to do it, but it's reasonable, right? So let's say your data was this. Your data is 0.2, 0.1. So these are two dimensions, right? The second data point is 0.5, 0.2. Third is 0.65, 0.1. I'm just making up numbers, but I'm trying to follow what it is there. 0.4 and 0.7, 0.6. So let's say these are my 5 points, right? So one possible way is to just represent it using the first dimension. So 0.2, 0.5, 0.65, 0.4, 0.7, right? However, there's of course this is not a very good way to represent it. Why? Because you're losing a lot of information, right? So whenever you are reducing dimensionality, you always lose some information. So a broad goal of any dimensionality reduction method is to minimize that loss, right? So you want to go from 2 to 1, but you don't want to lose. But when you do this, right? So what essentially you're saying is that I'm going to project all of my data on this line, right? So now I give you this data, but using this, you do not get the sense of the other dimension at all, right? Because you have completely ignored it. Another option would be to project it on this line, and then you're losing a lot of information along that, right? But still, if you see this, right? So if I project it in this line, both of these dimensionality reductions are different. You can compute some errors saying how much have you lost, right? But let me give you an example. So let's say another example was your data looked like this. It was fairly like in this dimension there's a lot of values, but in this dimension the variance is very less, right? So if I project it in this direction, you get these points, right? These whatever number of points. If I reduce it in this dimension, right? So you got all these points over here. So which, in your opinion, is better embedding, a better reduction? The one projecting in this direction, right? Why? Because just intuitively it seems like we are losing less information, right? Because you're projecting it here, you still get a sense that okay, the data is spread like this. However, if you project everything here and then I give you these values, then you don't get a sense of how much the variance is, right? So even with this sort of trivial reduction, there is some notion of which one to go for, right? So mathematically you can actually formalize it. You can say we want to reduce it in that direction in which the variance is maximized. Okay, so you want to go in that dimension in which you are trying to in the reduced dimension the variance is still high, right? So remember, the variance is nothing. Let's say these are my so I'm going to call these xi's, right? So x1, x2, x3, x4, x5, and these are reduced, so I'm going to call them z1, z2, z3, z4, z5, right? So the variance, when you compute variance in this one-dimensional space, will be nothing but, and let us assume that they are all centered. So let's say there is no mean at all, right? So mean is 0. So it's going to be zi square summation 1 over n, right? Typically it's zi minus mu I, but if I ignore the mean for now, right? Which means that there is some mathematical reasoning behind which dimension to go for, right? Now it turns out, so the idea is that you want to, when you want to reduce in a direction that gives you the maximum variance. Now it turns out that you do not always have to embed it in one of these dimensions, right? What you can come up with a line, any line, straight line, and embed the data in that direction. Right, so now, so the new space will be one-dimensional because everything is on this line, but the direction of this line is not horizontal or vertical, but it is somewhere in middle, which essentially means that this line is nothing but a linear combination of these two directions, right? So if you remember your vector geometry, right? Typically, sometimes we call this I direction and j direction, right? So you can think of this line as some linear combination of this, so alpha I plus beta j, right? So the idea behind principal component analysis is to find the direction of the line such that if we project our data in on that line, so projecting data means that if let's say the equation of this line is u, and I'm putting a caret symbol here, which means that it's a unit vector, right? So to denote a line, all you need is a unit vector in that direction. So if you want to project this point, let's say this is x, bold x1, all you do is you multiply x1 dot product with mu hat, right? So this is the projection. Right? So the idea is that you can project, or you want to find the line, the direction of the line, such that when you project the data points here, it gives you the maximum variance. All right? So let me give you another example. I don't have it here. Right. So for example, let's say this was your data, right? Again, two-dimensional data, right? So in this data set, one option would be that you project all your data on this line, or you project all this data on this line, or you draw a line that goes like this, right? And you project the data on that line. And it will turn out that if you project the data on that line, right, the variance will be maximized. Sorry for that. The variance on that direction will be maximized. So the idea behind PCA is to find those lines. All right? Any questions so far? Yes. So you're saying, why don't we come up with a function that works both ways, which is invertible, right? And yeah, but the problem is, how do you learn that function? Right. So what we will see is that PCA is kind of that, and even like factor analysis, right? So you can think of it as a bijective function because you can go from z to x and you can come from x to z. But the point is that given just the data and without making any assumptions on the function, it's hard to come up with that function. But actually, so that's a very good point. So actually PCA, and we'll come to that a little while later, is sort of a bijection because what it gives you is a linear combination. So you can think of that function as a linear combination of your x's. So it gives you z, and then you can give the linear combination of z and go back. So you can do that. But then you're implicitly making an assumption that that function is linear. So that becomes an issue at times. All right, so this is sort of a motivation, right? So let's go back. Where are we? Right. So the best way, of course, as I said, to embed data in one dimension is to go along the line that gives you the maximum variance, because that gives you the best spread, right? So you don't lose, you will lose the least information in that case, right? So that is the reason. Now, what is that direction? How do you find that direction, right? So we can do that mathematically. So let's say we assume that this is the direction, right? U. So this is a vector U in two-dimensional space, because your line will be in the d-dimensional space, your original space, right? So, and it is this caret on top because we say that it is a unit vector. So the projection of any point xi, it should be xi, is given by this, right? This is the projection on that line. Now, if you want to find the direction, what you want to find, because we are following this principle of maximum variance, is that we want to maximize this value, right? Here I'm making an implicit assumption that the mean is 0. So typically when you do variance, right, we have to divide by, subtract by mean as well. But so just for mathematical or notational, simplicity, I'm ignoring that. So we are trying to maximize this variance of the data set, because we not only have 1 point, we have 5 points or n points, right? So this can be written as, I just expand it, so it looks like this. Okay, if I just rearrange the term and I move the u outside, because u does not depend on I, so it looks like this. The reason I'm writing it like this is because now this looks like the sample covariance of the data set. So if I have the data set in which I'm assuming that the mean is 0, and which can be easily done if you have a data set, if I just subtract each column by the column mean, then the mean of each component will be 0, right? So let's say we have already done that. That is also known as centering the data. Then this looks like the covariance matrix. So now we want to maximize this quantity, U transpose the covariance matrix. Let's call the covariance matrix S U, right? So we want to maximize this. There is only one constraint here, that U, the magnitude of U is 1. It's a unit vector, right? So it's not a direct minimization, it's a maximization, but it is a constraint maximization. You want to maximize this given this constraint, where S is just this. So S is just what you compute from the data. And my ears are ringing for some reason. It's too close. All right, good. So how do we do that, right? So we have to maximize this, and we can do that very easily because we know the principle of Lagrangian multiples, right? Or multipliers. All right, so let's try to do that. Right. So finding direction of maximum variance, right? So the idea is that you're trying to maximize this function, which is U transpose SU, which gives you the total variance of the embedded data, subject to a constraint that U transpose U is equal to 1, which implies that U is a unit vector, right? So you want it to be a unit vector. That's it. Where S is nothing but the variance of your data set. Transpose, right? So you go back, you can see that this is how you compute the variance, right? So how do you do this optimization, right? So think of this as a constraint, right? And we have seen that the way you solve constraint optimization problem is to rewrite this with a new objective function in which you introduce a Lagrangian multiplier, right? So this is a Lagrangian multiplier times the constraint, right? So we want to, so this is an L, which is a function of both U and S, lambda, right? Because we are trying to find U, which gives you the maximum variance, right? So now what we do is we can differentiate it with respect to both U and with respect to lambda, right? So you can say if I differentiate with respect to U, what you get is S times U, actually it will be 2S times U minus 2 lambda, and all of these calculations. So I'm doing basically d by dl of U, right, is equal to this. And this you can, if you want, you can look up matrix cookbook and this will give you these identities, right? And now we set it to 0. So when you set it to 0, we get, right? So we want to, the answer, the right answer, the direction that will give you mu, U will be the one that maximizes this, all right? Or one that satisfies this, right? So if you start looking at this now, S is a D cross D matrix, right? This is a covariance matrix, right? And both U of course is a D cross 1 vector, and lambda is a scalar, right? So if you go back to your linear algebra class, you know where I'm getting at, right? So the solution for this would be S cannot be equal. See, S is a matrix. We want to find a solution that satisfies this. The solution is a U. We want a U that satisfies this. Eigen. So I hear eigen, so I take that. So this solution with this would be eigenvectors of S, right? But there can be d eigenvectors of S, right? So which one should we take? So if you remember, any eigenvector, let's say there is an eigenvector UE, it will satisfy this and it will have a lambda UE, right? So lambda is the eigenvalue, right? So what if you go back and see here, if you put U as the eigenvector which satisfies this, you will see that the total variance here, where is the variance here? Because if this is the solution, then SU will be lambda U, right? So then it will become lambda times U square. So let's see here. So let UE be any eigenvector, okay? Because there can be d eigenvectors. What we are trying to say is which one is the best answer, right? So it will be any eigenvector. So then the variance, total variance, will be equal to what is that? U E transpose SUE, right? Because that's the total variance. But since it's an eigenvector, so this is actually equal to this. So this will be U E transpose lambda UE, right? Lambda is a scalar, so I'll bring it here. And this, because it's a normal, it's a unit vector, so this is 1, right? So it's just nothing but lambda E. So there are d possible solutions, but the eigenvector that will give you the best maximum variance is the eigenvector which has the highest lambda E, right? So which means that the direction we want is the eigenvector with largest eigenvalue, all right? And that is also known as, this eigenvector with the largest eigenvalue is also known as the principal component, or the first principal component. So which means that if I give you a data set, and if you just center it and then you compute its covariance matrix and you find its eigenvector which has the largest eigenvalue, then if you embed your data in that direction, that will give you the maximum variance. All right, so that is the best direction to embed your data in if you want to get the maximum variance. Right now, your objective might change. Like instead of maximum variance, let's say you say, I don't care about maximum variance at all, I care about something else. Then maybe this is not the right answer. But if maximum variance is what you want, which is a reasonable thing to expect, then you go for the largest, you go for the eigenvector with the largest eigenvalue, which in this context is also known as the first principal component. Then somebody asks you, can you give me two directions, right? Maybe I want to embed it in two-dimensional space. Then you take the two largest values, right? So essentially what you can do is you can take all your eigenvectors, sort them by their eigenvalues, and the first one, and then you can pick 1 or 2 or 3 if you want to reduce the dimensionality to whatever number, right? Any questions so far? Yeah. Uh-huh. Right. Yes. So because if you remember, right, when you want to project your data, all you do now is take the inner product. So what now your data, you take your data point and you do its inner product with this unit vector, which essentially means you are projecting it on a line, right? So U gives you equation of a line. When you do this inner product, this, sometimes you can also write it as this, right? Then that gives you where it falls on that line. So you're embedding it in that one-dimensional space. All right? Any other questions? Yes. 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 So the notion of variance is a spread. So you're trying to maximize in that you want to preserve as much information as much information as you can, right? So variance kind of is a mathematical or statistical way to quantify that notion of information. Yeah. Right, right, yeah. Yes, yeah. So the question is, can the variance in the reduced space be more than the variance in the original space? The answer is no, because that's the maximum variance that you can have. So if you don't reduce your data at all, which essentially means that if here, right, if you choose all of your eigenvectors and reduce it in the d-dimensional space again, then you get the same data. Then it will be the maximum, right? So in fact, yeah. So that's a very good question. So that comes to the next point. Laptop, HDMI. Right. So the question, the point is that now you can take the first principal component, you can take the second principal component, right? And then each principal component, so there is a total variance of the data, all right? Each principal component explains some part of the variance, right? So if you take the first principal component, it will explain some part of the total variance. If you take first two, then it will add both of them, and then so on. So the variance that each principal component explains is given by the eigenvalue, right? So which means that if you sum these things up, that will be the total variance. So if you only choose L, then you are explaining only part of the variance, right? So this is the total variance, the denominator, because here you are taking all of your principal components. See, there could be D eigenvectors, right? So there can be D principal components. So this is the total variance, and this is the variance that is explained if you only take first L, right? And why do we take first L? Is because when we take first L, we are mapping our data, which was in d-dimensional space, into L-dimensional space, right? So that is the idea. So now you can do this dimensionality reduction. So what we do is we only take the first L eigenvalues and vectors, right? And then we construct this new matrix W, okay? Now W has D by L matrix. So in W, there are L columns. Each column is a eigenvector, all right? So think of W as collection of all the directions. And then what you can do is, if you do X times W, you will get this Z, which will essentially be mapping the data which was originally in, so X is a data matrix, right? So X will have N cross D. It has N rows. Each row is a data point in the dimension. When I multiply N cross D times D cross L, I get an N cross L matrix. So each row in that new matrix Z is the reduced data point in the L dimensional space. So each input vector is replaced by a shorter vector. All right, any questions so far? All right, very nice. So this is sort of the algorithm. So if you want, if I say, hey, here is some data, run PCA on it, these are the steps that you need to take. You want to center the X, because in all of our analysis, we assume that data is centered. Centered means that if you take a column, which is one variable, it should have a mean of 0. So that can easily be done by doing a column mean and just subtracting the data by that, right? Then you compute your S. Sometimes I write S as this, sometimes 1 by N. There is a difference, but it doesn't matter too much, especially when the data is large. Then you find the eigenvectors and eigenvalues for S. Then you sort them. Then let's say you know what your L is, then you only extract W, and then this gives your lower dimensional embedding, right? Embedding is again not a good word. Lower dimensional reduction of Xi. Any questions so far? All right. So now we are going to look at it more from the latent variable perspective, right? Because I've introduced this notion of W, right? So this now starts looking much like a loading matrix that we talked about in factor analysis, right? So you can think of PCA as a crude form of latent variable model in which you assume that X, any Xi, is just Z, sorry, any Xi, you have some Xi that you observe D cross 1 vector, and you can think of this as a linear combination W times Zi, right? Because this will be a loading matrix which is W transpose. So this is a D cross L matrix, right? And this is a L cross 1 vector. No, it was W. Sorry. So you can think of this as your latent LVM, latent variable model, which means that there is some hidden variable, which is Zi, and what you observe Xi is just a linear combination. The reason I don't call it latent variable model is that there are no probabilities here, right? In latent variable, typically you assume that we get a PDF of Xi given Zi, but here it is a direct model. So we say Xi is just a linear combination of your Zi, right? And then what you can do is, if somebody asks what is Zi, so Zi will be just the inverse of this Xi, right? Because if I bring it here, but it turns out since W transpose W is identity, right? Because this is all the eigenvalues are orthonormal to each other, right? So if you remember eigenvalues, each eigenvalue is orthogonal to each other, right? Which means that this is this, which means that Zi will also be just, so this is that bijection that you were talking about, right? So you can go from here to here, you have some random variables, some hidden latent variables, you can go to your observed, and you can go from observed to hidden, right? So that is the idea. So this is the connection between latent variable models and PCA. Then typically what happens is that then you introduce this notion of a PDF. You say, okay, the PDF of Xi is mean centered, this is the mean, and then there is some variance, and typically the variance is given by some sigma square I, and then it becomes a probabilistic PCA. All right, so but that's just for you to just get a flavor of, but if you want to understand it more, then we can talk about it later, but that's not part of the scope of this course. All right, so that is the idea. Now you can also think of PCA, as I said, right? So now this is the latent variable model, right? That we know some hidden variable, latent variable, and we have some loading matrix, and we can reconstruct the observation, right? The reason we call it reconstruction is that because we learned this W from the data, right? We had some data. Now, did I say? Yeah. So W is the matrix with some L eigenvectors, right? So we learned this from the data. So if you remember the algorithm, right, we had X and then we learned this W, right? But now, if I give you some latent variables, you can reconstruct Xi, right? So what will happen is that there is a theorem called classical PCA theorem, which says that if you compare this reconstruction with the original value, then this squared error, right, that will be the minimum for PCA. All right. So if I come to your door tomorrow and I give you a data set, right, and I say embed it in a two-dimensional space, okay, you can run PCA or you can do anything else, right? There are a bunch of ways to do that. But then I say reconstruct my Xi's using this embedding, okay? And I want a solution in which if I take my original data and I compute its error with your reconstructed data, it should be minimum. Then PCA will give you that minimum. All right, there is no other way that will give you minimum. The only way to find the value, the reconstruction which gives you the minimum error is through PCA. Okay, that's called the classical PCA theorem. So the idea is that because what you're doing is you're essentially mapping data into new space, right? So you had a d-dimensional space. Now you are trying to find a new space which comprises of L dimensions, right? So each dimension in this new space is given by a basis vector. That's what we call. So each eigenvector is a basis vector, right? So this goes into more of matrix algebra. So when when you're transforming a data a space, right, a coordinate space. So typically we assume that this is a coordinate space, a three-dimensional x, y, z, right? If I rotate it, then I have a new space, right? I can also compress it and I can stretch it. I can do many things, right? All of that can be done by using some basis vectors, right? So the idea is that if you reduce W if you reduce your X into a L dimensional space, then the best answer in terms of this reconstruction error will be given by PCA and nothing else. All right. So that is the idea. All right. So now we'll look at some sort of demonstration behind PCA, which is very interesting. Otherwise, that's sort of the conclusion of the theoretical aspects of PCA. Any questions so far? All right. So now let's maybe these things will make it more clear. So let's start with this example, right? So I said that here is this two-dimensional data set. So if you do PCA, right? If I find the first, so this is a way to find the eigenvalues for a data set. So sigma is your S, okay? Sigma is the covariance matrix. So these are the two eigenvalues and these are the two eigenvectors, right? So now what you can do is, one thing you can see clearly is that these two eigenvectors are orthogonal to each other, which means these are basis vectors. I mean, they are perpendicular, that is true, right? So now if I, no control, all right. So these are the two eigenvectors. If I plot them, right? So these are the two eigenvectors. So if I plot them in the data set, this is what it gives, right? So I'm actually scaling them by their eigenvalues. So what this tells you is that if this is your data set, if you project it in this direction, then that will give you the maximum variance in one dimensional. And then the second direction would be this. Okay? So that is the idea. I don't know what this is. Let's forget about this part. Okay. So now let's see how to use it for some analyzing data, right? So let's look at our favorite, the digit data that you're looking at, right? So let's say I'm only interested in looking at the number 3 digit, right? So this is one of the 3-digit data, right? But in reality, your data is in 784 space, right? So that is your D, right? Now, if I perform PCA on it, okay, so there is a, in sklearn, there's a code called PCA, but you can also do the eigen analysis and do PCA as well. So if you get the data, right, so the first thing that you get with PCA is, the first thing that you need to see is how many principal components should I take, right? Because there will be, in principle, D principal components, but only a few of them might be useful. So how do you find that, right? So you want to find the principal components that are explaining enough of the variance, right? So that is done by what is called a scree plot, right? So what you do is you plot the lambdas, which are the eigenvalues, okay, and sort them and plot them, right? And then you also normalize them so that they are between 0 and 1. So what this tells you is that if you take only the first eigenvector, right, it will explain maybe 7% of your data. All right. If you take, let's say, the first 10 eigenvectors, then it will capture this much variance or explain this much variance. So this gives you a notion of, okay, how many eigenvectors should I choose? So for example, if you choose the first 200 principal components, right, that pretty much explains most of your variance, because after that, the eigenvalues are very small, right? So the first step is to use this scree plot to say, okay, what is my L? How many principal components should I take, right? So here I am saying, let us just use the one principal component. All right. So here, in fact, I must have run it. Oh, let's say I run it with just one. Okay. So of course, then if I take one dimensional principal component and then find my Z, which means that instead of representing my data in 784 space, now I'm representing it only one dimensional space, right? So then what I do is I find my hidden variables, right? So that is just XW, as I said. And then I find the reconstruction, which is ZW, right? So I'm trying to reconstruct data in this 784 space. And then if I plot it, this is what, this is the original one of the digits. So I'm plotting one of the digits. So this is one of the digits, and this is how it looks like if I reconstruct it. Okay. So of course you can see there's a lot of difference, right? Because you have lost a lot of information. You were representing your data only in one dimensional space, but it does seem to capture some of it. All right. But if I increase it, let's say instead of 1, I say, let's look at top 100 dimensions, because if you look at the scree plot, it that kind of explains it pretty well. So now you see that the reconstructed image starts looking like this. But what the classical PCA theorem says is that whatever L you choose, right, the difference between these two, the square difference between the values in these two images, will be minimum if you do PCA. You can't do better than that. All right. And then of course, if you choose all of the principal components, then you get the best, all the variances explained, which means that the data looks exactly like what your data is, right? So that is the idea. Now you can also see, so you can also use it to sort of look at all of your data. So let's say I load all of my images here, right? And then I do 3-dimensional PCA, and then I project it in this 3-dimensional space, right? So this is what it looks like. So the color indicates the digit, okay? So all the dark blue are some digit, all the red are some digit. So this gives you, as I said earlier, right? So if you want to visualize data, right? The data is in 784 space. All you can do is visualize a digit at a time by doing that reshaping. But ideally, you want to visualize all of the data together. Then PCA lets you do that, right? But of course, what you see here is you don't see clear clusters. It's not like all the 1 digits are here, 3 digits are here, 4 are here. The reason being that in 3-dimensional space, you're losing a lot of information. So things are getting clubbed together, but you still see, right? All the same colors are in one place and so on, right? You can do it in 2-dimensional space as well. You get this beautiful plot. Ooh, too big for the browser to render. But anyway, so that you can look at it later on as well, right? Yeah, I can stop here. I do want to give you another demonstration of using PCA for face recognition. So maybe we'll do that next time. So when you look at face, right? So every face, you can think of a collection of faces. So every face is like a digit, right? It's an image, but you can flatten it. So that's the data in that space, right? If you do PCA on that, then each principal component in that terminology is also known as eigenphase. So each principal component, they call it eigenphase, but it's nothing but a principal component. So this is a paper which came out in 1992, I think, which is face recognition by eigenphases. So there they demonstrated how to use PCA to do face recognition by doing this dimensionality reduction, right? So we will look at that example maybe in next class. Any questions so far? Yeah. Yeah. Okay. So the question is, can you do PCA for feature selection? So what PCA does is that you are reducing data from D to L. So you are doing what we call feature transformation, right? So feature selection, it could have many meanings. So one of the meaning of feature selection is that you have D dimensions and you want to select some of the most important features. PCA doesn't exactly do that. What it does is it transforms them. So it creates or 4 or whatever L new features. Each feature is a linear combination of your original feature. What you can do then is try to eliminate all the features that do not figure in any of the features. You can do that part, but that's not a direct effect, maybe a post processing. We can talk more about that later. Yeah. So when we PCA, it is basically the set of principal components, right? And ordered by their importance. So how much variance. So to do that, what you do is you take your data and you compute this algorithm, right? So you compute the covariance matrix of your data, right? All you've been given is the data, nothing else, right? So you compute the covariance matrix, you find its eigenvectors and eigenvalues. Now each eigenvector is one of the principal components, right? So you sort them by their eigenvalues and then in a decreasing order, of course. And then the first one will be first principal component and so on.